project. So, but also I would like to briefly mention some numerical simulations and X-ray observations as well. So yeah, who am I? Yes, I'm Takuya Akahori, and oops, sorry. Yes, originally I was a theorist, so I carry out the kind of the numerical simulation, hydrodynamic simulation in the supercomputers, and some predicted some observable quantities from the numerical data. But more recently, I'm working on the radio astronomy. I observed some cool radio jets, and I collaborated with my postdocs and then discovered something like interesting radio features. Okay. Then, yes, I briefly introduce my research. One is the magnetic turbulence, the other is the magnetic reconnection. Then I mainly want to focus on the physics, but I also introduce some observational results on the ABS-2C22, CZ1410. Those clusters are our targets in today's talk. So I think I don't need to explain in detail about the background of what is our universe, but you know that the standard lambda CDM cosmology predicts that our universe are formed from the small teeny quantum fluctuations, and then we experience inflation, big bangs, and then structures are formed from the density or temperature fluctuations. They're like this. Then yes. Galaxy clusters formed at the nose of the large-scale structure, or the cosmic web, so-called. Then, in the galaxy clusters, we know that there are a fully ionized gas that is called the intercluster medium. The temperature is around 10 to the 7 to 10 to the 8 Kelvin. The density is about 10 to the minus 4 to the 10 to the minus 2, or even the 10 to the minus 1 at the center of the cluster. And the metallicity is about 0.1 to 1.0 solar abundance. So then today this ICM is the main player of my topic. But of course, when we talk about the clusters, galaxy clusters and ICM, the quite important kind of player is also the galaxies, of course, especially the radio jets. Significantly impact on the evolution of the properties of the ICM. So this is kind of the quite beautiful pictures of the AGN jets in the galaxy clusters. Now, I think one of the most famous, popular one is that AGN jet at the center of the pulsar clusters. Then the blue shows the X-ray map, so meaning that the ICM distribution. And the red one is AGN. Then you know that the AGN jet make kind of feedback to the ICM, and then we see some so-called ripples in the cavity of X-ray. Then those structures is believed to be made by the central AGN jet activities in the past. And also the right one is that the recent results of the low-power observations of the Karma cluster. That this is the main galaxy clusters, and then this is the subclusters, and then we see the kind of beautiful emissions, most of all of the clusters environment. And then when we zoom in, then here we believe that this is AGN jet, but this is so-called wide-angled tail galaxy. But well, it's basically the AGN jet makes a tail, and then it connects to this diffuse radio features. We believe this is caused by the shock. Then the shock accelerates the cosmic rays. But this AGN jet may contribute to the cosmic rays to the shocks, and then effectively the shock particles are accelerated. Okay. And also then in galaxy clusters now, the kind of non-thermal aspect is quite key. Because in the last 10 years, 20 years, the scientists have studied the thermal part very much. But the non-thermal part, such as the turbulence, magnetic field, the cosmic ray, is not well known yet. So for example, this one shows a merging galaxy cluster. I forgot the name of this cluster. See the one 1359 point something. Please see the Clark's paper. And the blue shows the X-ray surface brightness. So that there are two clusters. Then these clusters are now trying, attracting each other. And this is a early stage merging galaxy cluster. And then we discovered this diffuse radio emission, diffuse synchrotron radiations. Interestingly, this emission is linked to the X-ray detected shock front with a Mach number of 1.3. So that's really interesting. And this one, we found unknown diffuse radio emission at the center of the Abel 1060. Then we call this the flying fox, but the origin is unknown. So then now, thanks to the quite high sensitivity and high angular resolution radio telescope, yes, SK precursors like Meerkat, ASCAP, LOFA, and so on. Now we can find lots of unknown new things. Then those things are basically tightly linked to the non-thermal aspect because this is synchrotron emission, so that this is evidence of the existence of the magnetic field and the cosmic rays. And then many people believe that particle acceleration can be made by the turbulence now. So first, I focus on the magnetic turbulence a little bit more. Then I just briefly introduced one numerical simulations made by the duetter 2008. So the magnetic field generated that amplifies in the last structure formations of the universe. Then in the structure formation, we know that there are vortex and shocks. Then at the curved shocks, and by barochronic term, magnetic field can be generated by the so-called Biermann battery effect. Then, so this is the numerical simulation, and then I think the clusters around here, then this is large-scale structures, and then there are many shocks with a Mach number of 10 to the, say, 1,000, depending on the place. But then these curved shocks can generate the magnetic field and then immediately strongly amplified through the small-scale turbulence dynamo because there are vortex and the large eddy can cascade into the small eddies and then stretching the field lines and amplify the magnetic field strength. Then, so this means that the part of the kinetic energy is converted into the turbulence energy. Then turbulence energy can be converted into the magnetic field energy. So then this paper predicts that this turbulent energy is, say, 10% or so at the cluster environment with the temperature 10 to the 7 to 10 to the 8, while that is, say, quite comparable. So that thermal energy and the turbulent energy is comparable at the lower temperature region. That is the largest structure or warm hot intergalactic medium. Then, so that the turbulence can amplify the magnetic field, so-called small-scale dynamo. And the growth of the turbulence experiences 3 stages. First one is exponential growth and linear growth, and the last one is the saturation phase. And then kinetic energy decreases in time, magnetic field energy increases in time, like this. Then the estimation predicts that the magnetic field energy is around 10% to the 40% of the turbulence energy. So these simulations say that, yes, so the magnetic field is ubiquitous in the cluster of galaxies, or even the large-scale structure of the universe. Then, based on this numerical simulation data, so I carried out some, mock observations, meaning that I integrated numerical data and then make a mock observational map of the Faraday rotation measure. This is defined like this. Maybe you know that. Then we realized that there are cosmic rotation measure background. So when we observe the high resistance sources, more or less the background polarized sources experience a Faraday rotation caused by the large-scale structure, a magnetic field in the large-scale structures, like this. Then I just show you a more recent numerical simulations by the BATS groups. And then these guys compare the origin of magnetic field let's say that there are roughly 3 types of the origin of magnetic field. One is that the origin at the early universe. So that in the early universe, the magnetic field was generated by some exotic scenario. Then the second one is actually the small scale turbulence diagram I introduced. The last one is also important is that the AGN feedback, so that the magnetic field generated amplified in galaxies at first. Then this amplified magnetic field leaked to the intergalactic space by some galactic wind, AGN jet, and so the ramp pressure slipping, and so on. So compared to the 3 models, so they found that actually the difference of the origin of magnetic field remain on some level in the current universe. So then it's quite interesting that the observational, examination of the magnetic field of the nearby universe will say something about the origin of magnetic field in the universe. For example, they claimed that mean magnetic field strength depends on the mass of the halo. The mass of the cluster, the mass of the group of galaxies. But the dependencies are a little bit different. So the magnetic field is proportional to the mass to the power of 0.15 in the primordial magnetic field origin model, proportional to the mass to the 0.4 in dynamo model, and then mass to the power of 1.8, so in astrophysical origin. So this is quite interesting. So also, the existence of turbulent magnetic field is claimed by from the observations. Then this is I just bring one example. This map is basically the radio jets. So I think the central host galaxy is something like here. Sorry, I don't remember, but somewhere here. And then jets blow up, then show some structures like this and like this. But the map shows not the synchrotron intensity, but the rotation measure, Faraday rotation measure map. So look at this. We are here. Then there is a polarized radio galaxy. Then this polarized source passes through the intercluster medium, which is magnetic turbulence, so that we see some pattern of the rotation measure like this. So interestingly, that these authors compared this rotation measure map with the numerical models. So they consider the turbulent magnetic field and then changing some parameters, and then compare the pattern, like for example, the power spectrum of rotation measure or structure function of rotation measure with the observed one. Then what the conclusion is that actually this observed map pattern of the rotation measure can be explained by the Kolmogorov life scaling. So this is strong evidence of the existence of turbulence. So I don't explain in detail about this something like blah blah blah. But the key point is that the ICM is actually magnetized plasma, but the magnetic field strength is not so strong. Magnetic field is not so strong, and then most likely the ICM behaves like just a hydrodynamic fluid when we consider the relatively large scales. But if we take a look at a little bit sub-kiloparsec scale or parsec scales, then we enter into the MHD regime, and in which the magnetic field is important. So more recently, the Japanese X-ray telescope satellite CRISM was launched, and then it's really a game changer of the turbulence study, because CRISM can directly measure the turbulent velocity of the ICM from the observation of the lines, for example, the iron lines, Doppler shift, and the Doppler broadening. For example, let's see the number, the velocity dispersion, that's say 150 km per second, and Virgo 160 km per second, Hydra, and then 100, 180, blah, blah, Perseus cluster, 150 km per second, level 2029, and blah, blah, blah. So then, at the moment, kind of, how to say, measure discussion point is that the major turbulent velocity is a little bit weaker than that's expected from the numerical simulation in the past. So yes, so that's still under discussion. So that I don't know. Maybe some is due to the selection bias, but some is due to the missing of some physics. So anyway, quite interesting phase now. All right. So now I move on to the first key target cluster I built to switch to. So this cluster is a little bit far, redshift of 0.2 galaxy cluster. Then this cluster has elongated XM morphology along galaxy distributions. Then here is the central galaxy, AGN. By the way, this is a meerkat image, so around 1.3 gigahertz. So this is central AGN jet, red lobe. And then we see the quite interesting feature here. This is actually the wide-angled tailed galaxy, but shape is really, really interesting. So it looks like an omega shape. Yes. So what's this? This is the key question. So that Kohei Kurahara, Dr. Kohei Kurahara, my collaborator, investigated this cluster, this AGN jet and cluster using the different many escape precursor pathfinders, for example, upgrade GMRT, ASCAP LUX, Meerkat, and ATCA in Australia. Then, so we see that actually this jet has a kind of straight feature and a curved feature, and then something like a tangled here. So yeah, quite interesting. And we found that the perpendicular field is predominant for the straight jet part, like this part. That this is just show the multi-field direction like this. So it's basically perpendicular to this straight bar direction. So maybe that we expect that there is a kind of spiraling magnetic field here, right? Okay. And we check the spectral index map because the spectral index maps provide us the information of the aging or the acceleration of the cosmic rays. Then we found quite cool results. So then this is a kind of the radial profile, the distance and then intensity and index. The distance is that we measure like this, so that we made a distance along the feature this of a watt galaxy like this. And then we found that some difference between the northern jet and southern jet. Then blue shows the southern jet profile, then orange shows the northern jet profile. Especially please look at the bottom figure. This is the spectral index, while the southern jet shows a kind of smooth steepening of the spectral index, meaning that the cosmic ray is aging. So the high energy particles lose the energy at first. They're changing the spectral index steeper. But northern jet, they show something like more constant spectral index, right? Then we compared this with the numerical simulation of the jet propagation like this. And then what we found that actually this simulation considers the accelerations, continuous accelerations along the jet propagations. Then we found that, yes, this one. So we see some, almost constant spectral index if we consider the continuous reacceleration of the cosmic rays along the jet propagation. So yeah. Okay, so the inside of the jet, so we know that there are turbulence and then some kind of tangled field and also shocks. So maybe that the particles are accelerated at these sites in jets. Yeah, but again, the interesting feature is that at the southern jet, we don't see this continuous acceleration. So it's quite a mysterious result. Then, okay, back to the interesting feature of omega shape. So that we compared it with the numerical simulation. The conclusion is that the simulation do not predict the omega shape. So yeah, looked at this. Then in this simulation, we consider the kind of flow of ICM from left to right because this galaxy is falling into the center of the clusters, so that this galaxy feel the wind of ICM, and then some land pressure is happening here. Then so that jet launched towards the north and south, but it go toward the downstream of ICM like this. But we don't see the omega shape, especially that actually we see some curve and then going outward and some twisting here, but we don't see that this omega, actually this omega curve. So then this omega curve means that more or less we need a force toward this direction, right? Force. But the simulation doesn't predict any force to the, to the inside direction. So it's really mysterious. So what's the origin of this force? It makes curves like this. Then, yes, we discussed some physics. One is the Kelvin-Helmholtz instability. Now, actually, the Edding turnover time is around 200 mega year. This is basically consistent with the growth time scale of the Kelvin-Helmholtz instability. So that, yes, the KH happens around the bending point. So that's okay. Then we claiming that, okay, this omega shape is made by the twin vortex. So what is twin vortex? So, the growth of turbulence depends on the Reynolds number. Then high Reynolds number make quite well-developed turbulence, While the small Reynolds number fluid doesn't make any turbulence, just it's a kind of well-aligned flow. Then there is a critical Reynolds number. Then in the case vortex is formed above the critical Reynolds number of 46, then this is actually the experience around the critical Reynolds number. Then around the back downstream, we see the twin vortex here. Then if the Reynolds number is larger than 46, some the Kalman vortex like this can arise. But around the critical Reynolds number, we see that this kind of special pattern, and then inside this part and this part, some vortex exists, a twin vortex exists. So if this shape is made by this twin vortex, we can predict something like interesting physical parameters. For example, kinematic viscosity coefficient can be calculated like in this calculations, in this equation. And then we can, estimate that this Reynolds number is close to the critical Reynolds number of 46. Then we obtain the kinematic viscosity of the galaxy, coefficient of the gas ICM. That's really interesting. Okay. So the next one is the magnetic reconnection. So this part actually we recently submitted our SKAO science book. Then my chapter just recently accepted, so then you can look at my paper in the future once it is published. So I think that not many of you are familiar with the reconnection. I just start with a quite kind of educational, quite a simple one. So what is the reconnect? Sorry, this is turbulence, not the turbulence. This is reconnection. What is reconnection? So let's think about the magnetic tube, magnetic flux like this, like this, but the direction is opposite. And then if the two field line goes close each other, and then this field is the topology is changed because the energy is lower than the this one. So this one's energy is lower than this one. And this is a magnetic reconnection like this. Okay. The magnetic reconnection is actually happening in our universe. Then the most popular one is the aurora phenomena. So you can see that the schematic movie. This is the solar wind, and then it hits to the Earth's magnetosphere, and then magnetic reconnection happens like this. So magnetic reconnection happens in the daytime, like here, and also it goes to the night side here. The neutral current seeds get formed, and then reconnection happens like this. And then accelerated particles go along the Earth's magnetosphere and they go to the polar regions and then make aurora, Sorry, this is some text, but I'd like to read. So the ideal MHD. Ideal MHD is that the fluid moves together with the particles. Then it is frozen in the magnetic field. Then ideal MHD condition is clear. The ideal MHD condition is that the electrical conductivity is quite large. Then magnetic diffusivity is close to zero. Now, actually, then the high temperature plasma is known to possess a large conductivity. So it's actually the ICM is as well. So ICM is believed to satisfy the ideal MHD conditions. In the last 30 years or 40 years. Then ideal MHD has a high Reynolds number, magnetic Reynolds number, and a high Planck number. Then it is known that the ideal MHD cannot reconnect magnetic field lines. This was discovered, say, 60, 70 years ago. So that the ICM is believed to satisfy the ideal MHD condition, so that the reconnection never happens in the ICM for the ICM with a quite high Planck number or high Reynolds number. Therefore, in the last few tens of years, so the many galaxy clusters, researchers never consider the reconnection in galaxy clusters because this is really unlikely. But recently, I observed this galaxy cluster and then realized that maybe magnetic reconnection is needed to explain what I observed. So this cluster is a nearby galaxy cluster. Then this is an overview of the cluster, and then we see some central radio jet and then interesting neighbor jet. Then the main players here. And the central diffuse source, MRCB 1407-425, is an unknown source. And then we observed this with Meerkat, GMRT and ATCA. And Meerkat Galaxy Cluster Legacy Survey observed this one. So like this. So you can see that, this is a radio lobe, I believe, because there are central, point source here, and then bipolar shape, it looks like radio lobes. But the interesting feature is this one. At the northeast part, we see some extensions. I define it as a northeast cape. Then we see the factor of 4-5 brightness jump around here. Then I define this as a cliff. So it looks like there are two kind of structures. The main radio lobe plus something like additional emission. Okay. Then the spectral index map shows the deacceleration at the cape. So that I number 1, 2, 3, 4, blah, 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 16. And then AGNs here. And then near the AGN, we see the quite symmetric spectral index change. Then we can explain this as the aging of the jet, the cosmic rays in the radio lobe. Radio lobe expanding, and then the outer side has a more younger cosmic ray, and then inner side has older cosmic rays, meaning that the aged one has a steeper spectral index, so it looks to be okay. So the important part is here, from the 10 to the 15, around here. So actually, the spectral index is steepening, so aging. But suddenly, the spectral index is flattened, meaning that the particles are suddenly accelerated here, around 30 to 14 here. Okay, so this is very interesting. So why cosmic rays are deaccelerated here? Is that a really question? Then I realized that this cape aligns with the X-ray pattern, so-called the X-ray sloshing pattern. So the background red-blue is the X-ray surface brightness residual map. Residual map means that we subtracted the mean X-ray surface brightness map from the observed X-ray surface brightness map. So this is residual. So we clearly see the pattern here. So this is so-called sloshing structure. And then this cape is well aligned with these sloshing structures, like this. So it's really cool. Like this, So this cape is along the contact discontinuity of the cold gas and hot gas. Okay. The more interesting feature is that the polarization angle is perfectly aligned with this cape. So that this by the magnetic field direction, so that the magnetic field is really aligned to the cape. And the polarization fraction is also interesting. Here we see the super high polarization fraction of about 70%. So this is basically consistent with the alignment of the magnetic field here. And then I think that this is contact discontinuity, so that the magnetic field is more or less compressed or stretched, and then make a quite aligned magnetic field, compressed magnetic field, and then making the quite high polarization, linear polarization. Sorry, yeah. All right. So that yes, I discussed the origin of the Northeast Cape. Then actually, I said that this is this is contact discontinuity, but actually, still some shock is possible. But well, so the future X-ray observation is the key to distinguish these origins. But I like to push the cold front case. Then. So then the tracking the stretches and align the magnetic field like this, and then see the magnetic field go into this region, and then maybe at the cold front magnetic reconnection takes place because of we expect that in such kind of the compressed aligned zone of magnetic field, neutral current seeds can be made. So the neutral current seeds is the key to make the magnetic reconnections, right? Then, yes, we actually have another possible site of the magnetic reconnection in this MRC 0600-3399 So this is in the central part of the Abel 3376 galaxy cluster. And the James is the first author of this paper. So maybe the most of you guys know this paper. So we focus on this part. So that the spectral index is steepening. So cosmic rays aging. And it suddenly stop. The meaning is that some deacceleration is taking place. And then again, aging here. So that around here, the cosmic rays are deaccelerated. Then again, around here, the cold front contact discontinuity exists. So that at the cold front contact discontinuities, maybe the magnetic reconnection is taking place. Okay, like this. Then magnetic fields around the 10 microGauss is predicted based on the numerical simulations. Then here, the important key parameter is the plasma beta. Plasma beta is a ratio of the thermal energy, thermal pressure, thermal energy, and the magnetic field strength energy, or thermal pressure, the magnetic field pressure. But anyway, that's close to 1. So this is really, really key point of the magnetic reconnections. Please remember the magnetic plasma beta value, like this. Okay. So okay, let's think about the reconnection. But as I said, ICM is ideal MHE, so that ICM never make a reconnection. So that how we have to say confront this question. Okay, so let's break the ideal MHD condition. Resistive MHD. Actually, the buoyant plasma motion could break the frozen condition. Then magnetic field diffusion can take place. This is a well-known feature. Then nonlinear evolution of magnetic reconnection depends on the magnetic diffusivity. And then the solar physics, there are two types of the basic model of the magnetic reconnection. One is the Sweet-Parker, the second one the Pechek. But I don't explain in detail, but these Sweet-Parker and the Pechek reconnection model cannot explain the reconnection in galaxy clusters, expected reconnection in galaxy clusters, because the time scale is super, super long. It's a super long, longer than the time age of the universe. So we need some more effective, fast reconnections. So that the situation is exactly the same in the solar physics. So that the reconnection is a key, but the making reconnection is quite difficult. We need something advanced theory. Then recently, I found a quite key numerical simulation or a PIC simulation, particle cell simulations. Then the author's main interest is a magnetic reconnection in turbulence. But I think that this theory can be, we can adapt this theory to the cold front for the magnetic reconnections. Then what they consider is the plasmoid instability, which makes the fast reconnection. Then I don't explain the plasmoid instability, but I forgot. Oh, I forgot to attach the figure. Okay, anyway, well, like this, I maybe no one I can understand, but how to say? It is kind of the mode of the plasma, and then this is a little bit kind of new theory, modern theory to realize the fast reconnection. So sorry, I forgot the figure, but anyway, so please, yeah, just agree that the plasmoid instability is a possible origin, possible explanation to make a fast reconnection in galactic clusters. But however, the key point is that in this simulation, if in order to realize this plasmoid instability and the fast reconnection, the boundary condition is that the plasma beta is unity, meaning that the magnetic field strength is strong enough, comparable to the thermal energy. Okay, but this is problem because we know that the average magnetic field in galaxy cluster is say the microgauss, while the temperature of the gas is around 10 to the 7 to 10 to the 8 Kelvin. Then if we substitute these values into the plasma beta definition, we obtain the plasma beta value of the order of 100 or 1000. So that the thermal energy is much larger than the magnetic field energy. So that these boundary conditions cannot be realized. Again, we have a problem. But we don't need to have the plasma beta value in the global scale. But at local scale, maybe there are some regions in which the plasma beta is close to unity. Then actually we see this kind of local low plasma beta in the numerical simulations. For example, this is a Balzer's cosmical simulation of galaxy clusters. Then actually there are turbulence, right? And then we see some regions has a strong magnetic field with order of the 10 microgauss level. So not global, but a local magnetic field can be reached to the 10 microgauss level, and then the plasma beta value is close to 1. Then these two figures are the results of the numerical simulation of the merging galaxy clusters. Again, at the contact interface, magnetic field is compressed and aligned, then amplified, so that locally plasma beta can reach to around unity here, around here. This is exactly that I'm thinking about it. So that at the cold front, magnetic field can be compressed, aligned, amplified. The plasma beta is close to unity. So that I think that the condition of the magnetic reconnection, which is the plasma beta is close to unity, is satisfied. So in the case of this jet and also this case, so yeah, so I think, well, this is a kind of a new paradigm shift. So the new theory that okay, magnetic reconnection can happen in galaxy clusters, but not globally, but a very specific area, like cold front interface. So I think now we just have 15 minutes. I think we need some question time, right? So that I think just briefly skip this part. But what I wanted to say in the last few words is that I think that this reconnection is also important to solve the so-called cooling flow problem in galaxy clusters. But I don't explain details. Maybe I can introduce next time. So this is the Perseus cluster, and it's a filament, and has a quite interesting feature, and then filaments like this, and those filaments are linked to the magnetic strength. Then like this, so this is a numerical simulation of MHD turbulence at the stratified media, and then we see there's something like this pattern, and then not globally but locally, we expect that the quite strong magnetic field, strong aligned magnetic field, then those are the expected site of the magnetic reconnection in galaxy clusters. Okay, so summary, magnetic turbulence and reconnection in galaxy clusters forecast. And I just briefly introduced two observational results, Everest 322, Caesar 1410. In the Everest 322, we saw the omega-shaped wide-angled tailed galaxy. Then we discussed the possibility of the KH instability and then Kalman vortex, especially the twin vortex scenario of the critical resonance number of 46. The Caesar 4010, we found the cape, aligned the cold front, and then magnetic reconnection is a possible origin, possible explanation to explain the reacceleration of cosmic rays. Obviously, these radio observations can be dramatically improved with SKI, with ultra high resolution and high sensitivity, so that in the coming years, so it's really, really exciting. So that, yeah, I'm very happy if you work with me in the future. Thank you very much.
Thank you very much, Akahori-san, for that very interesting talk. Yeah, I think this is quite good, and there are many areas we could use both already existing MIACAT data and future MIACAT plus data, future SKA data to explore the science around this area. So thank you so much. I will now open the floor for questions from the room. Anyone? Maybe in the meantime I can start. Oh, I see Francia. Francia, go first.
Can you hear me?
Yes.
Okay. Thank you for the interesting presentation. My question is on the Kelvin-Helmholtz instability. You said that it happens in the bending point. So I'm not sure how did you get that. So can you explain how did you get that result? And the Kelvin-Helmholtz instability, does it only happen in the northern jet or on both sides, on the northern and the southern jet?
Sorry, I'm not sure I get your questions. So that you were asking about the difference of this features of a spectral index profile.
Yeah, also how you determine that Kelvin-Helmholtz instability is responsible for that.
Yes.
Yeah. So that yeah, thank you for your questions. So that what the observational fact is that this jet is curved, straight jet is curved and tangled. So that we need some physical reason of that, and then just actually the land pressure also work to bend this jet, but the key point is that this is a little bit more twisted, so that some physics is needed. So we consider the Kelvin-Helmholtz instability. And then actually the from here to the bending point here, we consider the the speed of the jet is around the sound speed. Okay, then the time scale is comparable to the eddy turnover time. So then eddy turnover time is a kind of the representative time scale for the growth of the turbulence, growth of the instabilities. So Kelvin helps the instabilities. So that we concluded that okay, actually the jet launched to this direction, but spending around 200 million a year or so, and then KH is realized, and then some more unstable patterns that's made.
Okay. All right. Thank you. And my second question is on the slide 24. I'm not sure, I didn't understand what was the cause of the particle reacceleration in the source.
Slide number 24.
Yeah, slide number 24. Yes. The accelerations here. So that yeah, we see the change of the spectral index. Okay, especially the spectral index has become flat. Okay, so meaning that the higher energy cosmic rays, the number of higher energy cosmic rays relatively increase. So this means that we need more or less more or less acceleration of cosmic rays. But then key point is that there are no source of the new cosmic ray here. So that this is the reason why I'm saying not the acceleration but the reacceleration, because there's more or less cosmic rays propagating from the main radio lobe to the cape.
Okay. Oh, all right. Thank you.
Is this your answer? I'm not sure.
Yes.
Okay.
Yes.
Good.
Thank you.
You're welcome.
Yeah. So if you go to, just before I give Paul the opportunity, because I have a question on slide 25. If you look at the magnetic field, yeah, the magnetic field direction is quite straight. Is this measured with meerkat? Because my expectation, based on the figure on the polarization fraction, is that around the area where you have very high polarization fraction, you should have more magnetic turbulence. So the direction of the magnetic field should be very much random around that spot. Is that what you see? Do you have meerkat polarization information on this region?
Okay, the answer is that no, we don't have the meerkat polarization data. But yes, and also the angular resolution is not enough with meerkat, unfortunately. So this is a meerkat image. Then this is a compact array 5.5 gigahertz image. So that the beam size is like this. So that the ATCA is at higher angular resolutions here. Then, so that this map and this map are basically the ATCA's results. So then compact array detected linear polarization and then shows quite a high linear polarization and then quite aligned polarization angle. So yeah, of course, in the future, yeah, maybe I think that the meerkat extension would be great.
Yeah. 20 kilometer
years,
baseline from meerkat can
exactly
clearly
yes.
resolve
So
that.
yeah, I should propose. Yeah.
Oh, cool.
Now, of course,
Nice.
SKA is obviously.
Good. Before I ask my next question, I'll give Paul the opportunity. Paul, please. Yes, you're muted.
Oh, sorry. There we go. Thank you for the talk. And sorry, just a general question. Have you got any current projects with meerkat or any sort of a list of planned projects you would like to do with the SKA?
Yeah. So actually, yeah, I'm thinking about to propose the science verification observations using SKA in the future.
Okay.
Yeah. So as and I said, the Meerkat extension should be great for this specific work because of the higher angular resolution comparable to the ATC, I think. So yeah.
Okay, cool.
Then
Okay, thank you.
yes.
Okay, NJ?
Can you hear me?
Yes.
Yes.
Thank you so much, Akahori-san, for your wonderful presentation. I have two questions. The first
Yep.
one is, as it pertains to these magnetic reconnection events, do we expect to observe more of them in the early or the late universe? And is there maybe potentially a dependence on the density of galaxy clusters? That's
Right.
the first question. And then the second one is, when you are measuring your Faraday rotation measures, what assumptions go into, for example, constraining the, is it the electron densities? Yeah.
Okay. The first question is really interesting. So no one knows because this is the kind of the limitation of the numerical simulations. Still, it is really challenging to consider the magnetic reconnection in the cosmological simulations of MHD. Then, because of the lack of the lack of the spatial resolution and the lack of the physics, so that we don't know what is happening in the early universe, in the early state of the large structure formation. Yeah, so I think that's a remaining questions, and then yeah, in the future, I think we should address this. So that the answer is that yeah, we don't know, but maybe yeah, very important yeah, and key question. So the second question is the Faraday rotation measure. So yes, Faraday rotation measure is basically the where is the definition equation? Yes, yeah. The integration of the electron density and the magnetic field strength along live site, so that that these two physical quantities degenerated each other. But we have the X-ray observational data, and then X-ray surface brightness depends on the square of the electron density and then root of the temperature, and so that relatively the X-ray measurements provides accurate estimate of the electron density, so that we use this value and the rotation measure value, and then derive the magnetic field strength, average magnetic field strength along live site.
Okay, thank you very much.
Yeah.
Yeah.
So the rotation
Okay, I
measure
see.
provides us with the information of the magnetic field strength along live site, and then polarize the intensity or the total synchrotron intensity provided with provide us with magnetic field strength perpendicular to the line of sight, so that basically the radio observation can derive the three-dimensional magnetic field strength. That's powerful. Hello?
Thank you
Disconnected?
very much. Yeah, thank you very much.
Do you hear me? Hello?
Yes,
disconnected?
I hear you. Yes,
Yes,
I
we
hear
can.
you.
Okay, okay.
Sorry, I
Okay.
just kicked me out. Raul, I saw your hand up. Sorry.
Thank you, sir, for the lovely presentation. I just want to know, with regards to the simulation of the omega-shaped galaxy, is it an ongoing project, and will there be many more observations and parameters to consider in order for the simulation to resemble the omega-shaped galaxy? So
Okay, thank you.
detailed.
Yeah, good question. Actually, some guys claim that this omega shape can be explained by just a viewing angle. So that if we, rotate the three-dimensional this what galaxy, then maybe we can reproduce this shape. But I don't know. Then actually the simulation is performed by the Dr. Omura, but unfortunately he is now working in the private company, so he left from the astronomy academic side. So that well, we
I
don't
think he
have
works
any
for
further.
Samsung, right? So that's a
Yeah,
good job.
yeah. So yeah, I'm very happy if someone else, take over this numerical simulation. And then, yeah, I fully agree with you that this is just a result of the parameter set, so that we can change many parameters and then can make a different, pattern shapes. And such kind of parameter study is really important to understand what is going on, and also to understand the physics in this system. So yeah, thank you. That's an important question.
Yeah,
Thank
so
you,
that
sir.
follows with my second. Thank you, Raul. Sorry. That follows my second question because Omura-san made this simulation before the omega-shaped galaxy was discovered in Miyaka's galaxy cluster
Right.
data. So
True.
I think if this is remade now and you consider different condition in the ICM, then you
Right.
can have some reverse flow or some compression of what I see is the jet. The outside part of the jet is definitely weaker in the velocity flow, right? So if you have something compressing it in this direction, there will be stronger resistance near the launch point of the jet and lesser resistance on this part. So you can definitely bend the jet in this direction. But what you see in the legs of the omega shape is actually the ICM resisting the flow in this direction and compressing the jet. So maybe if we vary the conditions of the ICM, we might be able to reproduce this. And sadly, Umura-san is making big money in Samsung, so probably won't come back anytime soon.
Yeah. Yeah.
But I definitely think this is omega shape. It's not a projection effect because if you see the southern part of the omega shape is actually projected into the screen. So, and you can see it with the boosting of the intensity in the line of sight. So
Yeah.
anyway, it might interest you to know that we have found a second omega shape galaxy. And
Yeah.
Francia, who asked the question, the first question, is working on that.
Yeah.
Oh, awesome. Any other question or comment? I don't see any more hands. And we need to let Akahori-san go to sleep because it's very late in Japan now. Thank you so much for the interesting talk. And we hope in the next maybe 1 year or so, we will get some more updates from your research results. And that will be interesting to listen to again.
Maybe. Yeah. Thank you for the opportunity this time.
Thank you very much. And have a good night.
Thank you. Have a good day.
Thank you.
Bye.
Okay, bye-bye. Bye, everyone. Yeah.
Goodbye all.